Hi everybody, it's Professor Burns here, and I want to take a quick look at section 4.1 where we're just getting into some applications of derivatives. And in this section, we're primarily looking at some definitions and some things we want to look at when we're looking at the graph and how we can use the derivative to help us figure out what those special points are on the graph. So the name of this section is Extrema on an interval. And we're starting off by looking at a closed interval. So that is a little bit important here, that we're specifically looking at a closed interval. And when it's a closed interval, we call those extrema absolute extrema. So that's an important term. So it says, let f be a function defined on a closed interval I containing c. So f of c is an absolute minimum, and I didn't leave enough room here so you have to abbreviate, absolute minimum of f in that interval if f of c is less than or equal to every other f of x value in that interval. So in other words, really what this just says is as long as f of c is the smallest value in that interval, it's considered an absolute minimum. Likewise, f of c is considered an absolute maximum in that interval if f of c is greater than or equal to every other value in that interval. So in other words, if f of c is the largest value in that interval, then we call it an absolute maximum. Collectively, we would call these extrema or absolute extrema because it's a closed interval. So take a look at this picture as a little example here of what we're talking about. So I want you to notice we have a closed interval here from -1 to 2. So x values range from -1 to 2. So the endpoints are closed there. And so within that interval, the smallest value occurs right here at this dip in the graph. So that would be an absolute minimum in that interval. And then the highest value occurs over here at the right endpoint, and that would be an absolute maximum in that closed interval. If, on the other hand, we have an open interval, then there may or may not be an absolute maximum or an absolute minimum. So, for example, in this picture right here, notice this is an open interval because these are circles, open circles on the endpoints. So we have a lowest point right here, but we don't have a maximum point because where would it occur? There's no ending to this interval on the right side. Likewise, in this picture, we have a closed interval, but it's not continuous. And so we have a maximum at the right endpoint, but there's no absolute minimum. Again, where would it be if there's an open circle here? So this leads us to an important theorem that's called the extreme value theorem. And basically what the extreme value theorem says is as long as we have a continuous function over a closed interval, then there has to be a high and a low. There has to be both a minimum and a maximum in that particular interval. And we'll see where how we apply this theorem in just a minute. We'll see an example. The next thing I want to talk about is this special picture here. It says, what is the derivative at these 2 points? So in other words, we've got a continuous function, and right here, we've got a peak in the graph, or a hill, it says in the graph. And then right here, we have a dip or a valley in the graph. And what I want you to think about is if I were to ask you, what is the slope of the tangent line or the derivative at those locations, what would it be? And I hope you see that at this location, if I were to draw the tangent line, it would be horizontal. And so the slope there would be 0. Likewise, down here, if I were to draw the tangent line, it would also be horizontal. So the slope there would be 0. So the derivative at those locations, whatever those are, so in other words, f prime at 0 up here would be 0. And over here, f prime of 2 would also be 0. So there's a special name for that. That is called a critical number. And we're going to use that quite a bit throughout this unit. Let f be defined at c. If the derivative at c equals 0, or if the derivative there does not exist, then we call that, c is called a critical number. And a lot of times, critical numbers are going to occur, are going to play an important role in finding extrema in a given interval and some other factors as we go throughout this unit. So we want to be able to find those critical numbers. Let's do an example here. It says find the absolute extrema on this closed interval. So notice that this is a polynomial, so we know that this is continuous on all real numbers, and it's a closed interval. So remember what the extreme value theorem said. It says that if it's a continuous function on a closed interval, then there has to be both a minimum and a maximum, or in other words, an absolute minimum and an absolute maximum in that interval. So how do we go about finding them? Well, the first thing we're going to do is find the critical numbers. So remember the definition of a critical number. It's where the derivative either equals 0 or is undefined. So let's find the derivative for this function. So that's going to be 12x to the third minus 12x squared. So that's going to equal 0 at the critical numbers, and that's what I want to find. We're going to solve this equation by factoring. Notice they have a 12x squared in common. So I'm going to factor out a 12x squared, and that leaves me with x minus 1. So I wind up with two critical numbers. 12x squared equals 0, x minus 1 equals 0. I get critical numbers at 0 and at 1. And so then the next thing we're going to do to find the absolute extrema is we're going to check values. So the absolute extrema are going to occur at either a critical number or at one of the endpoints. So I'm going to set up sort of a little table here, and I'm going to say, okay, the left endpoint was at -1. Then there's a critical number at 0 and at 1. And then the right endpoint, notice, was at 2. So remember, absolute extrema are going to occur at the critical numbers or at the endpoints. So I'm literally going to take these values and I'm going to plug them into the original function and determine which one is the biggest and which one is the smallest. So I'm going to substitute -1 into the original function up here. So f of -1, if I substitute that in, I'm going to shortcut it here and tell you that gives you a value of 7. Then you're going to plug in 0 into the original function, and that would give me a value of 0. I'm going to substitute 1 into the original function. That would give me a value of -1. And then I'm going to substitute 2 into the original function, and that would give me a value of 16. Okay, so look at those four values. Which one is the highest? Which one is the lowest? So the lowest is going to be your absolute minimum. So we're going to say there is an absolute minimum at the location -1, and the value there is equal to, no, I'm sorry, wait a minute, hold on. The x value, rather, was a +1, this point right here. But the lowest, the y value, was -1. So it occurred at x equals 1 with a value of -1. And then the absolute maximum among all those values was at x equals 2 and a value of 16. So notice that the minimum occurred at a critical number of x equals 1. The maximum occurred at the right endpoint. And you can see a picture of this looking at the graph. So my minimum occurs right here. That was at the critical number in that window. My maximum occurred at the right endpoint. And so that's how we find absolute extrema. We'll do a couple of examples with this tomorrow in class.